This is our lecture number 12, and we will talk today about analysis and design of multi-variable control systems. The reality is this: any dynamic system, any physical process has more than one input and more than one output. In reality, the outputs or the controlled variables could be velocity and altitude of the vehicle and position of the vehicle and on and on, and temperature, of course, and on and on and on. And the input variables could be the control efforts, such as fuel flow, such as position of the steering surfaces, and so on. But among input variables, we must consider disturbances as well. And then we're having a very interesting situation. If we would look at the physical nature of the process, we should realize that a process based on the laws of physics could be described by a system of differential equations, probably high-order differential equations. And these high-order differential equations would describe how the entire combination of input variables affects this particular output variable, how the entire combination of input variables will affect the output variable number 2, and so on, so forth. Yes, we're talking about high-order differential equations. However, if we want to take advantage of the matrix vector or state variable approach to the control problem, we have to find a way how to rewrite mathematical description of the realistic process. We have to figure out how inside the bunch of differential equations we can introduce a matrix vector notation, how to introduce individual state variables and proceed with the classical state variable description of the process. However, in this case, we have to accommodate for the reality many inputs and many outputs of the process. And then I can tell you from the control point of view that if the number of inputs is greater than the number of outputs, and these inputs are control efforts, number of control efforts is greater than the number of controlled variables, we are in great situation. We should be able to achieve the control goal or achieve the required position, required acceleration, required temperature, and so on and so forth by many different combinations of the control efforts. And then there is a very interesting issue, how to choose a combination of control efforts that would enable us to minimize the cost of control. For example, minimize the amount of fuel we're spending, or minimize time for moving our process from point A to point B. You know, these topics are raised in optimal control, and optimal control is not part of our 462 course. It could be also the situation when the number of inputs or number of control efforts is less than the number of control variables. In this case, the control problem cannot be solved. And this is also a topic that we will avoid. We are interested in a very specific situation when the number of control efforts is equal to the number of controlled variables. In this case, we should be able, and I will show you how to do it, we should be able to solve the control problem successfully. Of course, I'm assuming that the process is observable and controllable, but this is not the point of our today's presentation. Then you have to realize that if we have several inputs, u1, u2, um, and if we have vector of outputs y1, y2, yl, then the entire interaction between the inputs and outputs could be described not by a single transfer function, but by the transfer matrix. In this transfer matrix, we have individual elements, and individual elements of the transfer matrix are particular transfer functions. For example, transfer function G11 describes the dynamics between the input number 1 and the output number 1 of the process. The transfer function G22 describes the interaction between the input number 2 and the output number 2. I guess the row of the transfer the row of the transfer matrix is associated with the particular output, and each column represents the dynamics between the particular output and input 1, input 2, input 3, but the row index is the index of the output, and the column index is the index of the input. All right, now, what about this column G11, G21, GL1? Obviously, this column represents effects of the input number 1 on the system, of the input number 2 on the system, input number M on the system. When I say on the system, I mean every single output variable of the system. Okay? And if I'm looking at the row, then this row describes how input number 1, input number 2, input number M affect particular output, in this case, output Y1. Yeah, you know how to perform matrix multiplication, and therefore, if you're looking at a particular output number I, then you should compute it as the sum of the effects of input 1, input 2, input 3, and finally input number M on this output number I. I guess this is a good example that would enable you to very clearly take a look at the description of a 2-input, 2-output control system, or control plant at this point. It has 2 outputs, Y1 and Y2, and this outputs through this transfer matrix related to 2 inputs, U1 and U2. And here I am giving you an explicit definition of this transfer matrix of the system. So, how to obtain effect on Y1? Effect on Y1 would be defined, or Y1 of S in the Laplace domain would be defined as this transfer function, G11 times the input number 1 plus transfer function G12 multiplied by the input number 2. And Y2 of S will be defined as transfer function G21 times U1 plus transfer function G22 times the input U2. So this is easy. And now I want to show you how to switch, how to convert this state variable definition, this transfer function definition, into a state variable definition, state variable description of our system. Let's work on it together. So first of all, I want you to pay attention at the transfer function G11. It is written right here. And I split it into a pole zero form. And the next you can see transfer function that belongs to the same column. Transfer function G21. It is written right here. The next what I want to accomplish, I want to establish a common denominator for transfer function G11 and transfer function G21 for two transfer functions that belong to the same column of the transfer matrix. And this is what I do. The common denominator actually is s plus 1 times s plus 4. So there is no specific changes in G11. It already has this required, the common denominator. But G21 should be multiplied by missing s plus 4. Look, I multiply numerator and denominator by s plus 4, and this is the new definition of transfer function G21. Let me take a look at the second column of the transfer matrix. This is G12, and this is G12 in the pole 0 form. Well, I guess not too many poles, but you can see clearly, not too many zeros, but you can see clearly the poles. And this is my definition of G22 in the pole 0 form. And you can clearly see that the common denominator supposed to be s plus 2, s plus 4, and s plus 9. And because of this, I will reform G12. I will multiply the numerator and the denominator by G plus 4. And this is done right here. So this is in the polynomial form. I have the same result. Now, my intention to have common denominator for transfer functions of the second column leads to multiplying G22 by s plus 9. I multiplied the numerator by s plus 9, I multiplied the denominator by s plus 9, and this is the same transfer function in a polynomial form. The same transfer function in the polynomial form. So right now I have established common denominator for transfer functions of the first column and common denominator for the transfer functions of the second column. And now what I did is nothing special. I have the original transfer function definition of our system, and look what I did. I factored out these common denominators. And I moved these common denominators in the column of control efforts. It could be done. So, did I make a mistake? Does it really work? Well, look at this. This is the original transfer function or transfer matrix description of our system. This is exactly what you saw in the beginning. Then what I did is this element and this element. For these two elements of the first column, I came up with a common denominator. To do so, I have to leave alone this element as it is, but the second element element to 1. I multiplied by s plus 4 and divided by s plus 4. No changes. Now, I'm supposed to have the common denominator for the second column. And I have numerator and denominator multiplied by s plus 4, and numerator and denominator multiplied by s plus 9. So no changes made. Why I'm doing this? Because my goal is to establish matrix vector definition for our system. So I guess I am not making changes in the system by establishing these common denominators for column 1 and column 2 of the transfer matrix. Listen, now I want to define for you two new variables. I will call u1 divided by u1 of s divided by s squared plus 5s plus 4. I will call it v1. v1 is completely artificial intermediate variable. I want u2 divided by s cubed plus 15s squared plus 62s plus 72. I will call it u2 of s. Again, this is a fully artificial internal variable. And now, since I have v1 established and v2 defined, I should be able to state that y1 of s is equal to this expression. Look, 2s plus 6 times v1 of s plus s plus 4 times v2 of s. You see it right here. And for y2, I will have 3s plus 12 times v1 of s plus s squared plus 10s plus 9 times v2 of s. It's written right here. Right here it's written. And of course, I can convert these expressions into the time domain. And you remember that multiplication by s is symbol of differentiation, and so on. Therefore, for y1, I have this expression. And for y2, I have this expression. What we do next? The next what I want to do is this. Do you remember? These were my definitions of v1 and v2. This is v1 and this is v2. This is expression for v1. This is expression for v2. I will write down these expressions. Look, you saw them before. v1 is defined as this, and v2 is defined by this expression. So what I am doing now, I am doing this multiplication, and look what I have. I have s squared times v1 plus 5s times v1 plus 4 times v1, and it's equal to u1. And the same you have here. S cubed times v1 plus 15s squared times v1 and so on is equal to u2. And now I will convert to the time domain these two expressions. Look, u1 is equal to this expression, and u2 is equal to this expression. It's very easy to do. Now I want to reform these two expressions. Look what I want to do. I want to define v1, second derivative of variable v1. It's right here. And I want to define third derivative of variable v2. And it's written right here. And then, and I believe you saw it earlier, you saw it in the direct decomposition of the transfer function. We did things like this. I will introduce the following state variables. Look, this is a second order differential equation. It looks like I need two state variables. And this is a third order differential equation. It looks like I need three state variables. So look what I do. I have state variable x1 equal to v1. This will take care of v1. I have state variable x2 equal to v1 prime. v1 prime is taken care of now. It is defined as x2. Now, for this part, I will have state variable x3 equal to v2 to address this v2. And I will have x4 state variable equal to v2 dot to address this derivative. And I will have x5 equal to derivative of x4. This will address v2 double prime. This was easy. And now I want to define x2 prime. What x2 prime is? x2 prime supposed to be second derivative of v1, and I have expression for second derivative of v1. So I will just rewrite this expression. I will rewrite using state variables x1 and x2. I also want to define first derivative of x5. First derivative of x5 supposed to be v2 triple prime, or third derivative of v2. v2 triple prime is right here. So I rewrote it using x3, x4, and x5. And at this point, I can claim that y1 is equal to this expression, and y2 is equal to this expression. Where it comes from? y1 is defined through variable v1 and variable v2, and derivatives of v1 and v2. y2 is defined through variables v1 and variable v2 and derivatives of these variables. And for all these variables and for their derivatives, I can use state variables, and this is what I have for y1 and y2. And now we are ready for the state equation of our system. State equation of our system is written right here. This is the fundamental matrix. This is the column of state variables. This is what we always call matrix B. Matrix B. It works all right. Now, these two equations I will formally define in the matrix vector form. This is what we call matrix C, and this is the column of state variables. So I showed you how to perform some algebra and convert transfer matrix based description of a dynamic system into a state variable description of the same system. And I will show you later that when it comes to control system design, using state variable notations is a much more powerful tool than the use of transfer function definition of the control plant. At this point, I want to switch to 4 techniques for control system design, for multi-input, multi-output, or multi-variable control systems. So at this point, let me go back to the multi-input, multi-output control system definition. I want you to take another look at this schematic. Now I want you to assume that the number of control efforts is equal to the number of controlled variables. What do we want to achieve when we design a control system? Let me assume that I have not done any system design, but I will just apply unit step at the input number 1. What should be observed in the system? You will see response in the output number 1. You will see response in the output number 2. You will see response in the output number 3, and so on. And I have to assure you that the settling times may not be acceptable at all, and the responses may not be stable at all, and the overshoots probably would be absolutely unacceptable. I guess the whole issue of stability may not exist. What is the ideal situation? The ideal situation is when I have independent and controlled access to output number 1, to output number 2, to output number 3, which means that ideally, if this is the reference, and if I would apply a unit step input at this reference input, I will see response only in the output number 1, and this response supposed to have the desired settling time and desired overshoot. This would be the ideal situation. And if I would apply step at the reference number 2, I will see response only in the output number 2 with the desired overshoot and settling time. And I would see no responses in all other outputs. So I want to have fully controlled, independent access to every controlled variable. This is the ideal situation. And in order to achieve this goal, I have to undertake quite sophisticated system design, and I will show you techniques for this design. And I want you to know that this design problem may not be solved in every particular instance. But in majority cases, you should be able to successfully assure independent access, independent and controlled access to each of the output variables. You know, the problem that I am referring to is known as the problem of decoupling control. When you apply input signal just at one of the inputs, and you see responses in all other outputs, it happens because the system is cross-coupled. Relationship between U1 and Y1 is known as the channel number 1 of the system, of the control process. The relationship between input number 2 and the output number 1, for example, is a channel to one of the system. And if you have total of, let's say, 4 inputs and 4 outputs, the system can have total of 16 channels. And all these channels are coupled in the sense that each individual input affects all outputs. It's not good for the control purpose. We would like to have input number 1 to affect only output number 1, and the transient process should have the appropriate dynamics. We want input number 2 to affect only output number 2 with the required dynamic properties. We want to do the decoupling control. This is a general transfer matrix of the system. By looking at this transfer matrix, you should realize that the dynamic system in question is cross-coupled. This input affects through this transfer function and this transfer function and this transfer function every single output. Input number 2 through this column affects every single output. It's no good. Cross-coupled system we have. What would be the ideal situation? The ideal situation would be if this system would have the same number of inputs and the same number as the number of the outputs, and if the transfer matrix would be diagonal matrix. In this case, input number 1 will affect only in output number 1, input number 2 would affect only output number 2. This is our goal. We want to build, generally speaking, a decoupled system. We have to work on it. We have to work on it. So, how the problem looks in the state space, in the matrix vector notation. This is the state equation of the system. This is the output equation of the system. You understand that we have to introduce a controller, and controller is responsible for the definition of control efforts. And you know matrix F is the matrix of the controller. Matrix W is the matrix of the controller. Our goal is to choose matrix F and to choose matrix W such that we would be able to solve the decoupling control problem. This is the matrix diagram of the multi-input, multi-output state variable system. And you don't have to be a rocket scientist to figure out the dimensions for the individual matrices involved in this description. And again, I want to assume that the number of control efforts are here. Number of control efforts would be equal to the number of controlled variables. And if we would look at the system as a whole, then the number of reference inputs should be equal to the number of controlled variables. And then you have to figure out how to create a system such that reference number 1 would give you independent access to the control variable number 1. If we would apply unit step at reference number 1, we do not want to see any responses except for the output number 1. And the response of the output number 1 should have the required characteristics. The same is true for the reference number 2, reference number 3, and so on. I will approach the decoupling control problem gradually. First of all, I want you to think of a very realistic physical system. Personally, I have experience of building a system of this type for a power plant burner, for the Millikan power plant. It's in Lansing, New York. Imagine that this is a very sophisticated, multi-variable, multi-input, multi-output controlled plant. You know, I want to come up with a controller. And it looks like this is the controller number 1 that would close loop for the output number 1. And this is controller number 2 that would close loop on the output of the controlled variable number 2. Controller number 3 closes loop on the control variable number 3. And look, what can we achieve with controllers like this? Controller 1, controller 2, controller number 3. The best what we, if this is a cross-coupled control plant, and if we would introduce individual control loops, we will not eliminate cross-coupling between channels. They are conventional controllers. Controller number 1 affects only dynamics of the output number 1. Effect of other control efforts on output number 1 will not be eliminated by a control loop like this. I would say that in a realistic control system, you will find many, I would call them local controllers. These local controllers do not eliminate cross-coupling, but at least they eliminate instability, and at least they can manage the settling times for the systems. So let me tell you this. If I would apply a unit step at the input R1, you will surely see responses in the output Y1 and Y2 and Y3. However, because of the controller 1, probably Y1 would reach the required value equal to the reference. However, Y1 will be also affected by R2 and R3. Okay? So, if I would have no input at R1 and R3, then R1 would let me achieve the required value in steady state in the output Y1, but Y2 will change and Y3 will change. What do I have to do if I want only Y1 to change? I have to figure out how to simultaneously apply signals to R1, R2, and R3 such that Y1 will change as a result of all 3 input signals. Y2 will not change and Y3 will not change as a result of all these 3 input signals applied. You can, with a system like this, you do not have clearly defined individual access to particular outputs. You have to manipulate all 3, in my case, reference inputs to achieve the desired effect. And because of this, without having any mathematical background for doing this, You need lots and lots of intuition and experience of the process operator. And the process operator knows that if I would change, let's say, fuel flow, temperature will change, but so will change the pressure, and the composition of exhaust gases will change. So you probably would have to come up with the change in fuel flow and in a change of the airflow and in the position of the some valves, so that predominant change will be in temperature and changes in these two outputs would be minimal. Lots of experience is required for this. And because of this, the problem is very challenging. And because of this, the decoupling control problem is a very desirable problem to be solved in a situation like this. Let's see how this could be done. You know what should be done? You shall not directly apply reference signals. Regardless of your tremendous intuition and experience, simultaneous manipulation of reference inputs will not give you a successful solution to the control problem. What you should do is to establish a mathematically defined pre-filter. And this pre-filter will be responsible for the values of the reference inputs for these control loops. So look, I'm saying do not try to apply references directly. Design a filter and make this filter responsible for the definition of reference signals. However, those inputs to the reference are at your complete control. And if this filter is properly defined, what will happen is this. If you will apply unit step at the input row 1, this unit step at the input of row 1 will result in increments of R1 and R2 and R3. However, these increments mathematically will be defined in such a way that only Y1 will change and Y2 and Y3 will stay the same. And again, if you would apply step to the input row 2, this input row 2 will be converted into the increments at R1, R2, and R3, such increments that simultaneously acting, they will change only Y2 and will not affect Y1 and Y3. So this would be a decoupling approach to our problem. And I have to tell you this, I put here some kind of discussion, some kind of mathematical definitions. They are not important. The important thing is the following. If you would choose this filter as a static filter, just static filter, its elements will not be functions of S, just the constant gains. And if you would choose this filter to be equal to transfer matrix of the controlled plant, where S is replaced by 0, you will have a very useful result. What will happen in this situation is known as the steady state decoupling. Steady state decoupling requires you to build a static filter and apply reference signals through this static filter. And this is the definition of the static filter. So it looks like your first step in achieving this goal is to get this transfer matrix, replace S by 0, get a square matrix, and then invert it. The inverse of this matrix will give you this filter W. And then, if you would be able to insert this filter W, you will achieve the a decoupling result. However, this decoupling result is known as the steady state decoupling. How this will work? Let's say that you have this transfer matrix. Let's say that you replaced S by 0 in this transfer matrix. Let's say you define the static filter equal to the inverse of the G where S is replaced by 0. What will happen? If you will apply unit step at row 1, this unit step will be converted into the set of increments. The set of increments R1, R2, and R3 will affect Y1 and Y2 and Y3 simultaneously. You may tell me, where is the decoupling? Not yet. But in Y1, you will have the residual effect, and this residual increment of Y1 would be equal to the magnitude of the step applied at row 1 input. In Y2 and Y3, you will see transient terms that eventually will leave no residual effect. With time, they will disappear. And I will repeat this again. Let's say you will apply unit step at row 3. This unit step being applied at the input row 3 will be converted by the filter into increment of R1, R2, and R3. These increments will cause changes, transients, in Y1 and Y2 and Y3. However, the residual effect could be observed only in the output number 3. In Y1 and Y2, these transient terms will eventually disappear, and there will be no residual effect. This is why we call this decoupling approach a steady state decoupling. It does not cause your system to be a decoupled system, but your system is decoupled only in steady state. In steady state, you have access to the desired output variables. It's independent access, but it is independent access only in steady state. During the transient time, you will see changes in all output variables. I don't know if I can say it better than I did. However, it is very good to keep in mind that the original system described by the closed-loop transfer matrix must be stable, and its dynamics must be acceptable, which puts a lot of emphasis on the skillful design of these individual controllers or local controllers. If you will not design them, the system could be unstable and dynamics could be purely unacceptable. The second requirement is strictly mathematical. If you will take the transfer matrix of the system G and replace S by 0, you will have to have a non-singular matrix. Otherwise, the inverse will not be acceptable. Couple of conditions. And of course, the number of inputs should be equal to the number of outputs. This is the necessary requirement. So I guess the best at this point would be to take a look at my numerical example, and each of you will have opportunity to build your own steady-state decoupling system, implement this approach, and test it in the simulation environment. Listen, I came up with a system that has 3 inputs and 3 outputs, and dynamics of the individual channels seems to be on the formidable side. I have to tell you that probably you had a controlled plant with 3 inputs and 3 outputs, and the dynamics of this plant probably was horrific, and probably several very smart engineers got involved in building local controllers, and because of the local controllers, they were able to stabilize to some degree, improve dynamics of the system. I don't believe that they could achieve any decoupling effects, but system became stable and settling times became acceptable. So this transfer matrix is obtained for the system with local controllers. It relates reference inputs to the output variables of the system. How these local controllers affected individual channels, I'm not prepared to discuss, but the decoupling is not eliminated. However, the dynamics became acceptable. Steady-state values are reached. Then what I have to do, I have to replace S by 0 in this transfer function. And I got this result. And then I had to take the inverse. Fortunately, this matrix is not singular, and the inverse exists. And then I use this filter to define reference signals for my system with local controllers. Look, this is what I implemented. Now, I have to tell you that our approach effectively is an open loop approach. Yes, here inside there are loops, but as far as our addition to the system, it's an open loop system. It's an open loop system. So, effectively, steady-state decoupling design is an open loop approach. All right. What you can see now is this. It looks like I applied reference equal to 1 to one input, reference equal to, I think it was 0.75 to another input, and I applied the reference equal to minus 0.5 to input number 3. My system works in the sense that every channel shows some transient processes, but eventually all these inputs settle. So it looks like the local controllers do work. Our system consists of several cross-coupled but stabilized channels. Stabilized channels. I guess this is good to look at this graph. What happened here is this. I applied unit step with the magnitude of 1.5 to the input, not the reference, but to the input row 1. As a result, this step with magnitude of 1.5 applied to the input row 1 causes increments in reference 1, reference 2, and reference 3 of the local control loops. However, as time approaches infinity, in the output number 1 of this system, the controlled variable number 1 settles exactly to the value of 1.5. All other two controlled variables show some oscillatory transient processes, but then they settle to 0. So, since I applied step with magnitude equal to 1.5 to the input row 1, I see residual effect only in the output variable number 1, and the final increment is equal to the magnitude of the step applied to row 1. In all other outputs, I see no residual effects. And I guess this is the continuation of this experiments. I applied step equal to 1 to input row 1, and you see no residual effects in other outputs. However, you see simultaneous transients in all other outputs. Here I did the same thing with the row 2, and so on. Yeah, you know what you can call this, and you know what, you probably would get a much better results when you will work yourself. This part of the simulation is done with a very old-fashioned simulation tool. With a MATLAB, Simulink, or Vsim, you will get much better results, much more good-looking results. Okay, but I want to tell you that as you attempting to get independent access to one of the output variables, you can see cross-coupling effects in all output variables, but in steady state they disappear. The residual effect will be only with the output variable that you want to affect. This is the steady state decoupling.